In almost all cases, the biggest analytical sample challenge is that the sample exists in a molecular complexity environment. Within the sample, you've got what you're looking for, the chemical species that you're looking for. But you also have so many other chemical materials or chemicals that you're not interested in. And these materials, are what you actually refer to as matrices. So whatever you're not looking for that is present in your sample is what you call matrices. Whereas the chemical species of interest, whatever you're trying to detect, is what you refer to as the analyte. Now the challenge is, in almost all cases, the matrices tend to get in the way and interfere with your detection of the analyte. Now, even more complex is the fact that in most cases, the samples that you're dealing with are fairly heterogeneous. Think about it, maybe you're trying to analyze phosphates in cow dung, or maybe you're trying to analyze, a drug in, say, blood. And so these materials tend to have heterogeneous composition of the chemical species, which means the chemical elements that are present are not evenly distributed in the sample matrix. And yet when you're doing analysis, you have to make sure whatever goes into the instrument, is fairly homogeneous. The sample composition, is the same throughout. So that adds, to the complexity, of chemical analysis. But even in cases such as urine, which is a solution where the chemical composition is homogeneous, meaning the chemical elements are evenly distributed, these samples, exist in a labyrinth, of molecular complexity. And so how do you separate, the analyte, from the matrices so that you're able, to get good analytical signal for what you're looking for? So that is the biggest, analytical challenge, separating, the matrices that interfere, with the analytes. Even say in the cases, of droplets, from the mouth. Of course, especially in these days when you're trying to detect viruses, maybe in micro droplets. Now, again, huge complexity in terms of what is present in those droplets, proteins, different types of organic compounds and so forth. So how do you go about then to solving these bottleneck, the matrix interference that are getting in the way of detection? Now I propose, two major approaches to do this. One, you can choose an analytical method, that is selective. You've got analytical methods that are sort of blind to the other interferences. And often this is the case, with sensors, because sensors measure single analytes and they are completely blind to every other chemical species, that is present to some extent. I should say to some extent. There's still a little bit of interference, but to a great extent, they tend to be fairly selective. A good example, is a pH sensor. If you take a pH electrode, and dip it in blood, despite the fact that, there's lots of other junk, that junk or matrices that are present in blood, largely, you're just going to measure the hydronium ions that are present in blood. And so that's a good example, of a chemical sensor, that is very, very selective to whatever you're looking at. Meaning, you don't need to separate, the matrix from the analyte, because, the method is blind to the interfering species. Now, it's a huge industry because you can design different materials that behave like enzymes. I think we all know that enzymes are very, very specific to the substrate, and the substrate is the analyte. And so we often try to mimic nature by designing materials that are very, very selective, to a target analyte, and that way we can make a chemical sensor for almost anything. And that's the basis, actually, of most of my research. Now, the disadvantage with chemical sensors is the fact that you need a sensor then for each individual analyte. And that's why you're in a lab, such as an environmental lab, where you're often dealing with so many different types of analytes, it becomes a challenge, to get a chemical sensor for each and every different analyte that you're interested in. Maybe another advantage though is that these devices, they are small, they're inexpensive, and often you can take them, to the field where you're doing the analysis. So that's one way of solving the matrix interference, the bottleneck of sample analysis. Now, the other approach is where you do separation science. This is where you separate the analyte of interest, from the matrices. And how do you do this? I think there's so many different methods of doing it. You guys know about column chromatography, for example. Where you load a column, say, with the silica particles, and then you pass, the sample through the chromatographic column. You can also do liquid-liquid extraction. You can also do supercritical fluid extraction. You can also do precipitation, for example. You can do crystallization, and so on. Now, in analytical chemistry, you're gonna see most of the work, most of the industry actually is in the separation science. This is where, most of the chemistry actually happens in analytical chemistry, all right? Now, these methods can be tedious, the separation science. These methods can also be expensive. And so for that reason, people have tried to do the automation of separation science so that it becomes less tedious and so forth, in form of especially chromatographic separation. And so you guys are going to come across, gas chromatographic detection method or separation method with detection, obviously, and liquid chromatography, which are the gold standards, in separation science. So you walk into any big industry out there, and be it environmental analysis, forensics, and so forth, pharmaceutical companies, chances are they've got a couple of GCs, they've got a couple of LCs. So I would say separation science actually is the biggest employer, as far as analytical chemistry, is concerned. And in the lab, you guys are gonna play, with a GC instrument. You're gonna play with an LC instrument and get data and then play with that. So based on the tools of trade, okay, analytical chemistry can be divided into classical methods of analysis or instrumental methods of analysis. All right, so things like traditional titration, things like volumetric analysis, things like gravimetry, things like, the titration again here with the Buren, those fall in the realm of classical methods of analysis. That's how we used to do detection of chemical analysis before the invent of instrumental methods, which only happened actually in the 1950s. So before then, people used to do a lot of, classical methods of analysis. But even things, like precipitation, things like crystallization, even things like liquid-liquid extraction, that a fairly wet chemistry technique, they fall in the realm of classical methods of analysis, okay? In the modern day, detection approaches, most people use instrumental methods of analysis. So this is where sort of we've largely automated, the classical methods of analysis, with things like gas chromatography, things like atomic absorption spectrometers, things like autotitrators. You don't have to use a burette anymore. You can get the instrument to do it for you. Things like inductively coupled plasma to detect different types of heavy metals. And so you guys, are gonna use instrumental methods of analysis, in these courses as well. And so maybe the question you're asking is, have classical methods of analysis then completely fallen out of favor? And the answer is no. You still use a lot of classical methods of analysis. And so a good chemist, actually has to tie both the classical methods of analysis and the instrumental methods of analysis. Indeed, the classical methods of analysis are often what people use to prepare the sample so that it can be analyzed by the instrument. Maybe you've got some dirt, a soil sample. Instruments, cannot take dirt. You need to prepare the sample classically, using gravimetry, volumetric methods, so that you can prepare the sample in a way that the instruments, can do the detection. So I'd like now to talk to you about the different steps then in the analytical process. Okay. Now, the analytical process, sort of as I have alluded before, starts with a societal problem. I'll give you an example. You've got, water or water from, say, Athabasca River. And so maybe the residents around the river would be asking, is the water safe, for consumption? Is the water safe, maybe even for swimming in? And so that is what the society problem is. And so when they bring that problem to you as the analyst or the chemical analyst, you will have to define that problem scientifically or analytically. So the residents are looking, is the water safe? But as a chemist, you have to think what's potentially present in water that is an indicator of water safety. Are there contaminants in the water? Well, are those contaminants, heavy metals? Meaning, are they inorganic or are they organic? Are they pesticides? Are they polyaromatic hydrocarbons? Are they organic? Or are they pathogens? Things like E. coli, and other types of bacteria. So as an analytical chemist, you have to define what you would be looking in that water, what you'll be analyzing in that water as an indicator, of its safety. And so you have to define the analytical problem that I'm gonna measure, say the organic compounds or contaminants, present in the water sample. When you define the analytical problem, the next step, is to determine the best method, analytical method, to do the analysis. If we do not have an official method, that is already out there, you may be forced to go to the literature, to try and figure out, from what others have done, can you use similar types of the techniques, to solve the problem. And so you have to do literature search on what others have done, to solve a similar problem or the same problem. Now, the next step when you determine the analytical method to use, at least on paper, is to go to the field, and actually do the sampling. Now, sampling is a critical step in chemical analysis because one indicator of a good sample is that the sample should be representative, of what you're trying to measure. Now, if you're doing homogeneous types of samples, such as a river, then you have to, it's less complicated, because sort of the composition of the chemicals are homogeneous, meaning they are distributed evenly, in the water. But yet you still have possibility to sample different locations, in that river. If you're dealing with, say, a soil sample, which is heterogeneous, you have to think, about how to sample in a way that you create a representative sample so that you can be able to, give a good result of what you're looking for. So sampling is key. How do you do sampling to make the sample representative of what you're trying to solve? Now, the next step in the analytical process is to do the sample preparation depending on the method of detection. Like I said, if at all you're doing, say, heterogeneous sample, you have to do lots of different steps. And these are often classical, methods, where you do, for example, the digestion, if at all it's a solid sample, to make it into a solution sample. And most instruments, take solutions, rather than solids. Maybe you have to do extraction. Maybe the sample is present or the analyte is present at very low concentration, and so you have to do pre-concentration, and so forth. So sample preparation, getting the sample ready, for instrumental analysis. This is the most tedious step. This is the most expensive step as well, especially in terms of time, the use of organic solvents, and so on. Now, this is sort of the step also where you need to have in mind most of the chemistry that you've learned. So there's a lot of chemical equilibrium at play for you to think what is the best method of extraction and so on. So you have to think about the nature of the compound you're analyzing, so that you can get a good method, to extract it. So you do that, the next step, would be the analysis using the analytical method of choice. There could be liquid chromatography, depending on the problem. There could be AAS, atomic absorption spectrometer, depending on the problem, and so on. And so as an analytical chemist, you need to know, what is the best analytical method, for the detection of the analytes that I'm looking for. And then lastly, you're going to have your signal and your data, how do you report it, to a non-specialist, how do you take the data you've obtained and explain it back to try and answer the general problem, that you had initially. So take note, of all these steps, in the analytical process. Maybe I'll give you a specific example. You've been asked to determine the amount of caffeine, or theobromine that are present in a chocolate bar. And you've got two types of chocolates. You've got the white chocolate and you've got, the dark chocolate. Theobromine is always present at different levels in cocoa. And theobromine, is a mood-enhancing drug. It's a diuretic, it's a muscle relaxant. And you also have the caffeine, that most of us are dependent on, which is a central nervous system stimulant, and most of us can do without it. And you can see the structures of the two are very, very similar. In fact, the only difference is that you've got an extra methyl group, with the caffeine, that is not present with theobromine. So in terms of the chemical nature, these two compounds are very similar, and they become very difficult to differentiate actually. So you have to really think, what the best technique that I can use, so that I can differentiate the two and also be able to quantify the two. Differentiate and quantify the two. So what do you do then? Chances are, what you have here is a solid sample. So it's certainly a heterogeneous sample. So the theobromine and caffeine are not evenly distributed in a chocolate bar. And so I need to make it, a representative sample. I need to make it a homogeneous sample. So I'll take the chocolate bar, maybe I'm gonna grind it, with a mortar and pestle. I'm gonna hopefully do solid phase extraction, with the right type of solvent. You have to think about the best solvent, that would dissolve caffeine and the theobromine. there's a lot of junk, there's sugars present, there are proteins present, so I need to try and do the separation of the proteins, away from the analyte of interest. So lots of volumetric steps, that I need to work on before I'm able, to do column chromatography, possibly using a GC, so that then I can do the detection with an appropriate, detection method. So gas chromatography always have a detector. Maybe the detector in this case, you can see it's a UV detector. It's a UV detector. Okay. And so in the end, you can see that I've been able to separate the two, the theobromine, and the caffeine, and I've got those peaks. Those are just peaks. What I'm interested in is to know the concentration, of caffeine and the theobromine. And to do that, I have to do the calibration. And you're gonna see the most important thing in analytical chemistry is actually calibration. So you need to calibrate, all the glassware that you're using here. So you need to calibrate them, if at all you're using a pipette, you need to calibrate it. If at all you're using, volumetric flask, you need to calibrate them, and so forth. And so in the next 2 weeks, of your labs, that's what you're going to be doing in the lab, knowing how to calibrate, your classical, instrumentation or equipment, that you use in the lab. Often, again, they are used for sample preparation in the modern day analytical chemistry, but yet very, very critical. Okay. Because you want to know, if at all I'm using a pipette and it's a 10 ml pipette, how much volume is it delivering? Is it 10.012 ml, or what is the calibrated volume that I'm trying to deliver? But you also need, to calibrate, the signal that you're getting from the instrument. Like I said before, the signals that you're getting here is just a peak. And so it needs to be calibrated so that you can relate the signal, the size of that peak, with the concentration. And so again, we're going to be doing a lot of work on how do you relate the signal to concentration, and that is what we also call instrument, calibration, which we're going to talk a lot of, in the next couple of weeks. And so in the end, the instrument calibration that you're looking for is the following: that you've got the signal and you're relating it, to the analyte concentration. In most cases, you really want it to be linear. You want the calibration graph to be linear, so that the signal increases in proportion, to the concentration. And that way then you're able to quantify how much of theobromine is present and how much of caffeine, is actually present, based on the signal, and then you can determine the concentration that way. Okay? So take note of this. Now, the data that you get, in almost all cases, it's a mean, meaning you have to run your samples multiple times to be sure. But in almost all cases, you also have the standard deviation. Never submit a data where you only give the mean and no standard deviation, because every instrument has got some bit of uncertainty. And so again, you must always give the mean with the standard deviation, of that mean, because instruments have got different uncertainties. So we really want to know, in what range does the true value lies. And so we need to represent, the data that way. I'll give you two sort of scenarios, that I would like you to develop the analytical process, and maybe it's better to do it schematically, so you do it exactly the same way like I've shown you, from what is the general problem, the analytical problem, the searching, from the literature, the sampling, how do you do the sampling to make the sample representative? You at all is a heterogeneous sample, what do you do? What do you do as far as the sample preparation is concerned? what's the right instrumentation to use, and how do you deduce the right type of data, to report to the client, that you're serving. So case number one, this tremendous increase in the use of hormones and antibiotics in livestock production. Now, some of these antibiotics, are things like sulfonamides, and so on. And some of them, they get excreted in non-metabolized form. Now, the cattle manure is often used as a fertilizer, or there's interest in using it as organic fertilizer. Because the cattle manure has got these antibiotics, we need to find a way of removing them, from the cattle manure. And so the question is, as an environmental chemist, you've been asked to investigate, the presence of the different forms of antibiotics or hormones that are present, indicate what type of sample material, that you're dealing with, which is a cattle manure, is it heterogeneous or homogeneous, and develop a cost-effective method, to detect the amount of hormones and antibiotics that are present. Maybe another good problem is, in 2005, it was a catastrophic here in the beef industry here in Alberta, with the mad cow disease. This was followed by a series of beef exportation bans, in the major exporting countries, for our beef. As a researcher, you've been asked to develop a method to detect the presence of the critical biomarkers, that are expressed in mad cow, the prion proteins that are overexpressed in mad cow diseased animals, often in the brain of the animal. So indicate what type of a sample material this is and try to detect the prion protein to try and determine, if a cow, has got this type of disease. So again, a schematic, of the analytical process. And so expect this type of questions, actually in the exam. So to conclude, before the lab on Tuesday, I'd like you to watch the following video links, that talk about the best techniques, for your classical techniques. How you're gonna do appropriate, gravimetric analysis. How are you gonna do, the weighing and so on, taking aliquot, pipette, best techniques, for using pipettes, best techniques, for doing pipette calibration. It's gonna be the focus next week, and best techniques for doing volumetric and transfers, improving your pipette technique, and also laboratory safety, so make sure you spend some time, to watch all those videos, and it's gonna get you started on what to expect, next week when you come to the lab. And so lastly, I like to acknowledge the fact that, those videos were provided, by other universities in what is now an open sharing approach of resources. And so I like to acknowledge, the fact that we've got those videos, to use for global training, of our students. And so see you next week in the lab. So make sure you review those.